Hi, this is Alice Conjamie Pollock. This is going to be a review of counting and probability because before we can work on probability, we have to know how to count. And since I'll be talking about racing and cards and dice and gambling, I painted my nails red for you. You're welcome. I just thought, hey, I should have them scarlet red because I'm going to talk about gambling. All right, the first thing you need to know is how to count something simple like this. If you want to buy a car and they offer three interiors, leather, vinyl, and plush, and with the three interiors, they offer five colors, I don't know, yellow, black, white, gray, red. And they also offer two transmissions. You can either get automatic or standard. If I want to know how many different cars you could make with those choices, I would take my three interior choices times my five color choices times my two interiors. 3 times 5 is 15 times 2. There would be 30 total cars that you could have. For example, you could have leather interior with a yellow car automatic, leather yellow standard, leather white automatic, leather white standard, leather, and I'm going to go through that on each of these. I'll have 5 branches. This is called a tree diagram. 5 branches for color, and then I'm going to come off with automatic and standard, automatic and standard, automatic and standard. And so if you read all of those, there would be 30 choices. That's actually called the fundamental counting principle. It says if you would like to find how many possible choices, take the number of each item's choice and multiply them together, and that'll tell you how many. So there'd be 30 cars. Now, what if I'm wanting to arrange letters? For example, let me take the letters Foxy. If I want to find out how many different ways can I arrange these 4 letters, here's how I think of it. Using my fundamental counting principle, I would say, how many choices do I have for the first letter? Well, if I'm pulling a letter down, I could either put the O, or the X, or the Y, or the F. So I actually have 4 choices for the first letter. Now once I pick a first letter, and watch, pretend like you don't know what it was. I picked a letter. Now how many choices do I have for the next letter? Well, I have 3. I was picking from 3. Now I've chosen it. How many choices do I have for the 4th letter? 2. How many choices do I have for the 5th? That was the 3rd letter. For the 4th letter, I have 1 choice. So if I want to know how many ways I can arrange those using my fundamental counting principle, 4 times 3 is 12, times 2 is 24, there's 24 ways. Now if you don't believe me that there are 24 different ways, you need to just write them all down. There's 1. There's another. There's another. There's another. There's another. And if you start doing that, you're going to find that there are 24 different ways to arrange those letters. Now, what if I choose the word dodo? Now how many different ways can I arrange those letters? Well, this is a little different because if I want them to look different, watch this. If I switch this D with this D, I still have dodo. If I switch this O with this O, I still have dodo, but I want to count that as just dodo. This is another arrangement. Now that one is different, but again, if I do this, I still get the same arrangement I just had. If I get this, I have the same arrangement I just had. So I'm going to have to do something a little different on this one. Now, in order for me to show you what we do, I need to show you a shortcut to finding this 4 times 3 times 2 times 1. The shortcut to that is actually to find 4 factorial. Factorial, by definition, says I'm going to go whatever number. If I want 4 factorial, I will do 4 times 4 minus 1 times 4 minus 2 times 4 minus 3 until I get to 1. So for example, 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, so now that I know that's what 4 factorial is, and it keeps us from having to do that long math, all that multiplication, especially if you want something like 99 factorial, you don't want to put 99 times 98 times 97 and so on. Now, you're going to be doing all of this on your calculator. If you have a graphing calculator to find 4 factorial, I would say 4. Then you're going to go math, probability, so you're going to have to come over to the right to probability, and then come down to factorial. Enter. And now I'll hit enter again, and notice it says 4 factorial is 24. Now if you're using a scientific calculator, you're going to need to find your x factorial or n factorial key. I believe on this one it's above, where is it? It's above the 3. I don't know if you can see it in this light, but it says x factorial. So on this calculator I would say 4, and then I'm going to have to hit second. And since it's above the 3, I'll hit the 3 and then hit equals, and notice I get 24. You need to learn your calculator. Google how to do factorial on your calculator. Now that I know that's how I do factorial, let's go back to Dodo. Now on Foxy, none of my letters were the same. Remember, I was choosing, but once I chose the F, there were none alike. So if I switch any of these, I get a different grouping. So I didn't have to worry about doing anything different on Foxy. It was just 4 choices for the first, 3, 2, 1. But on Dodo, I'm going to do the same thing. Since there are 4 Scrabble tiles, or 4 tiles, I would say, well, there's 4 choices, then 3, then 2, then 1. So that gives me 4 factorial different ways that I can arrange them. But the problem is, I don't want to count that one because it's the same. I don't want to count that one because it's the same. So we have a formula in mathematics for this that says divide by anything that is alike factorial. The number of something alike factorial. Since I have 2 O's, I'm going to divide by 2 factorial times, because there's actually this many ways I can arrange them alike, times there's 2 D's, so 2 factorial. Now again, remember these parentheses? Since I want that divided by the whole bottom, I would do this, which would actually give me, and you're going to do this on your calculator in practice, but whenever you do that, you get 6. Whoops. If you actually do this, watch, here are our 6. Well, no, you do it. I don't have time. I don't want this to be longer than it has to be. There's 1. There's 2. There's 3. And there's 3 more. Okay, so you can look at that. Now, what if I had Mississippi? M-I-S-S-I-S-S-I-P-P-I, M-I, crooked letter I, crooked letter I, humpback I. Do y'all remember that? If I want to know how many ways I could arrange those Scrabble tiles that are different, I would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 factorial ways I can arrange the Scrabble tiles that make the word Mississippi. But the problem is, if I switch this S with this S, or this S with this S, or this P with this P, or this I with this I, I'm going to get the same grouping of letters. So we have to divide out, how many S's do we have? 4. 4 factorial for the S's, times how many I's? 1, 2, 3, 4 I's, so 4 factorial for the I's, times, what else do I have? P's. Whoops, sorry. That'll be 2 factorial for the P's. And remember to put your parentheses. And actually, I didn't do that one ahead of time. But if you got the 6 there, you should be able to do this one. And I don't have time. I want to go to the next thing. All right. So make sure you get the 6 there and do this one exactly the same way. Parenthesis, 4 factorial times 4 factorial times 2 factorial. Make sure you put your 11 factorial divided by and do that. Okay, so that's arranging letters. Now let's talk about permutations. A permutation is something where order matters, and it's where I have to use every item once. Or I don't have to use every item, but I can only use an item once. For example, let's think of cars in a race. If I have 6 cars in a race, and I want to know how many ways these cars can come in and place, this is one way. Green came in first, then orange, then pink, and so on. Here's another way. Here's another way. If I want to know how many ways, we actually have a formula for that. And if you were in my finite math class, we would derive that formula. But I'm doing this for Math for Liberal Arts, so there's your formula. Actually, although I do make you use that formula in your homework for a few problems, on your test, I want you to be able to use your calculator. So one way I could do this is say, well, since order matters, this would be the permutation of 6 cars taken 6 at a time. On my calculator, and I'm going to do it on the graphing calculator, I would do it this way. I would say 6, go get permutation by saying math, whoops, let me move it over here, go over to probability, I'm moving to the right, come down to permutation, I'm not at probability, sorry, probability. Now I want permutation, it's the second thing, so I'll hit enter. Now I already said 6 permutation, now I want 6 cars finishing together. That would be 720. There are 720 different ways that these cars can finish. Okay? Now notice order mattered because this is a different way. Trust me, this is a second place and this is third place. It made a lot of difference to the green car and the prize money they won, depending on where they were. Now, what if I ask this question differently? What if I just want to know how many ways first, second, and third can be awarded? Again, I would say, well, does order matter? Yes. So this would be the permutation of 6 cars, 3 at a time. I want to know how many ways I could do this. There's one way. There's another way. It could be these 3 cars. It could be the pink and then the purple and the yellow. It could be the pink and then the yellow and the purple. It could be the pink, yellow, and orange. Do you see what I mean, that there are going to be a lot of these? So how do I find out how many? I'll do the permutation of 6 things taken 3 at a time. On your calculator, if you have a scientific calculator, if you have a PRB key, you'll hit PRB just like we did. So you would hit 6, then find your PRB, and then say 3. If you, or find the combination key, I'm sorry, I'm on a permutation. You'll find the permutation, it'll be above something, so I would hit second, so I would say 6, hit second, and then I would find my permutation key and hit it, and then I would say 3 and hit enter. If you need help with doing this, Google your calculator or take your calculator to one of the tutors, and they would be happy to help you with that. Okay. So when I do this, I will get 120. I want you to see the difference between the first one, where I was finding out how many ways I could arrange all 6 of these, where order mattered, because that's different. And the second way I did this was I said, how many ways out of these 6 cars could they finish first, second, third? Purple first, pink, then orange. Or I could have had purple first, then yellow, then pink. Or I could have had purple first, then green, then blue. Or I could have had orange first, then green, then blue. And I want to find out how many of those there are. There are 120. Now, I could go back to my fundamental counting principle on this one pretty easily and say, look, if I want to know how many ways those cars could place, 6 cars, how many choices do I have for first place? Well, remember I had 6 of them all together, so I had 6 choices for first place. Once a car comes in first, how many choices do I have for second? I have 5 choices left. So that one comes in, and then I have 4 choices. Whoops, 3, 2, 1. And whenever I do that, I get 720. Notice that is also 6 factorial. So if you do 6 factorial, you're going to see that you get 720. Now let's revisit the problem on the bottom. If I want to know how many ways out of those 6 cars can I have first, second, and third place, how many do I have to choose from for first place? 6. And I'm going to pick one, pink, because that's my favorite color. So it's going to come in first. Now how many choices do I have for second place? 5. Purple, because I like it best out of these. Now, how many choices do I have for third place? I have 4 choices that I could put here. Let's say it's this one. This is one first, second, third combination that I can have. Now, if I want to find out how many ways, 6 times 5 is 30, times 4 is, well, looky there, 120. So there's more than one way I can do this, and if you have an understanding, you can pick the way that works best for you. All right, again with the permutation, what was the key thing? Order matters. Now let's talk about something where order doesn't matter. Here is our formula. Again, we're not deriving it. You have a few problems where you're going to use the formula and plug into it. Let me tell you you're just going to use your calculator key, and it's just like the permutation key, so I'm not going to pick up the calculator again. You'll do it the same way. Now, when would I use a combination instead of a permutation? Let's take these same 6 tiles. See, I did my homework. I've done all this ahead of time. Let's take these same 6 tiles, and let's say your friend has 6 books, and you say, hey, that's it. You say, hey, I'm really interested in borrowing 3 of your books. And your friend says, okay, I want to know how many ways you could pick 3 books. Now notice, I can't just draw the underlines and use the fundamental counting principle on this. Why? Because when I did that, order mattered. But if you pick these 3 books, The Darkness Before Dawn, which happens to be a book I wrote, Twilight, and It, that is 3 books, but that's the same 3 books as these. That's the same 3 books as these. When I did my little underlines or my permutation, I counted this as something different than that. So this is a combination. Why? Because I only want to count this once. I don't care what order it's in. Those are the 3 books I'm getting. So I would say, well, let's find the combination of 6 things taken 3 at a time and do that on your calculator, and you would get 20. There are 20 different ways you could select 3 books. There's one of those ways. That's the same one way, same 3 books. To get a different way, I would have to pull in a different book. 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 And if you do that and find out every possible 3-book combination, you would get 20. Now, another thing I like to think about with this is like when you go to Luby's and you get vegetables, I wrote this out. If I have 6 vegetable choices here, and I say, okay, you're at Luby's, here are your vegetable choices. Notice new potatoes and mashed potatoes are different. Those are completely different, I know, because there are a lot of people that do not like mashed potatoes and they love new potatoes, or vice versa. Now, if I go to Luby's and I want to know, I'm going to start with these because these are the simpler ones. Out of 6 vegetables, how many ways could you pick 1? Well, you could pick corn, you could pick peas, mashed potatoes, green beans, broccoli, new potatoes. There's 6 ways. Out of 6 vegetables, how many ways could you pick none? Say, I don't want any vegetables. It's only 1 way. How many ways out of 6 vegetables could you pick all 6? I'd like all 6 vegetables, please. Only 1 way. Now, how many ways could you pick 2 vegetables out of 6? You could pick corn and broccoli, corn and green beans, corn and peas. By the way, peas and corn is the same thing. That's why I'm using a combination, because those would be the same. The order doesn't matter. They're going to spoon them both on my plate. I could pick mashed potatoes and peas. I could pick new potatoes and mashed potatoes if you're feeling really like you want a lot of carbs. So if I go through every possible way that I could pick 2 vegetables out of these 6, where order doesn't matter because peas and corn is the same as corn and peas, then I would get 15. And if you don't believe me, cut them out and write every possible way that you could do it, and you'll see there are 15. Now here's another time I would use a combination. That is, let's say that I have 10 people in my job. I have 10 people, colleagues that I work with, and I want to know how many ways I could form a 3-person committee to help the student, to help the Save the Pets organization. Out of those 10 people, I want to know how many ways I could pick 3. Now, it doesn't matter if I say Sam, Sarah, and Sally, or Sally, Sarah, and Sam. Those are the same 3 people. So order doesn't matter. So I would say out of 10 people, how many ways could I pick 3? When you do that on your calculator, you're going to see that there's 120 ways you could pick 3 different people out of 10. Now, that is a different question than if I say, out of 10 people, I want to know how many ways I could select a president, vice president, and treasurer. Because now if I say Sally is president, Joe is vice president, and Sarah is treasurer, that's different than Joe is president, Sally is vice president, and Sarah is treasurer. It's gonna matter to you which slot I put you in. So when I pick 3 people, president, vice president, treasurer, I also have to include what if they're vice president, what if they're president, they're vice president, and they're treasurer. What if they're president, they're vice president, and they're treasurer. So order matters. I have to roll through every possible way before I pull in another person and go, here's another 3-person president, vice president, treasurer. So order mattered. I would do the permutation of 10 things taken 3 at a time. Now I wanted to talk about a combination lock because students usually miss the questions on combination locks because the words are a little misleading. If I ask you how many combinations exist for a 30 number, you know the old master locks with 30 different numbers to choose from, without repeating. So in other words, if 5 is the first number, the second number cannot be 5. And if I have 520, then the third number cannot be 5 or 20, right? So if I want to know if they can't repeat, well, remember permutations deal with I'm choosing and they cannot be repeated. So I would say that would be a permutation of 30 things taken 3 at a time. And if you do the permutation of 30 things taken 3 at a time, you would get 24,360. I hope you're checking this on your calculator. It's a good time to practice and make sure you can do this. Now, there's another way I could have done that one without repeating. I could have said, if there are 30 numbers, picture 30 tiles with 30 numbers on them. How many choices do I have for the first number? 30. Now I've pulled 1. How many choices do I have for the next number? 29, because I couldn't repeat them. How many choices do I have for the next number? 28. If you do 30 times 29 times 28, that's what you get. Now, what if I can repeat? If I can repeat numbers, this is not a permutation. Because in permutations and combinations, I can't repeat anything. If I have 6 books, you've got 6 books. You can't take the same book twice, okay? If I've got 6 cars, the same car can't come in 2 places. So those are permutation, combination type problems. Now, you can repeat, which means my combination could be 555, or 515, or 252, or 225. In other words, I can repeat the numbers. If you can repeat, I would say, okay, it's not a permutation or combination. Let me think through it. You've got 30 choices for the first. How many choices do you have for the second number? I'm going to use my fundamental counting principle. Well, since I can use every number again, I've got 30 choices. What about for the third number? 30 choices. Because remember, it's possible I could do 555 because remember, you turn to the right, then you turn to the left, so I could go back to the left to it, and then you turn to the right, you pass it. All right, so that would be 30 times 30 times 30. 3 times 3 is 9 times 3, that's 27 with 3 zeros. So 27,000. Notice I have more possible combinations if I can use numbers more than once, because this one, 255, 333 is included. 555, whoops, 551, 555, and so on. All of those are included in this, whereas none of those were included if I said without repeating. Again, that one was a permutation because order mattered, and the reason I put this on here is because when people see combination lock, they think it's a combination problem, but it's not, because on a combination lock, order matters. So make sure you pay attention to what your problem is actually, the meaning of your problem. Don't just go, oh, it says the word combination. Okay, now let's talk a little bit about probability. Since this is a review, I'm going to give you just layman terms of probability. To find the probability of something, it's how many ways can you get what you want out of how many equally likely outcomes. Now, everything has to be equally likely. Like if I'm throwing dice, every number has an equally likely chance of coming up. Flipping a coin, everything is equally likely. So if I want the probability of flipping heads on this coin, I would say there's one way to get heads out of two possible things that can happen. So the probability of heads is 1/2. The probability of tails, 1 out of 2 possible things that can happen. The probability of rolling a 4 on a single die is one way to get a 4 out of 6 equally likely things. Now, if my probability of getting a 4 is 1/6, my probability of not getting a 4, that would be the complement, the probability of not getting a 4, well, you're either going to get a 4 or not get a 4. So if I do 1 minus 1/6, that would be 6/6 minus 1/6, which is 5/6. Notice 1/6 plus 5/6 is 1. 1 would be 100%. You're either going to get a 4 or not going to get a 4. So those two better add up to 1, or if I'm in percentages, they better add up to 100%. Okay. Now I want to talk real quick about something that I'm not really going to do problems with, but I want to show you. If I ask you for the probability of rolling the sum of 3 on a pair of dice, the probability of a sum of 3 on a pair of dice, I would say, how many ways can I get a 3? Well, I could get a 1 and a 2, but look at this. This is a different fall of the dice. I could get a 2 and a 1, and those are two completely different falls of the dice. So actually, whenever I do probability with dice, I always picture colored dice. So I go, how many ways can the first one land? How many ways can the second one land? The first one can land 6 ways. The second one can land 6 ways. Then there's actually 36 different ways that these dice can land. One of them would be 1/1, 1/2, 1/3, 1/4, 1/5. Then I'm going to flip this one to 2 and go 2/1, 2/2, 2/3, 2/4, 2/5 until I roll through all of them. And if you Google pair of dice images, you'll see they'll show you all 36 of them. Now, if I want the probability of getting a sum of 3, there's 2 ways I can get a sum of 3. This way they could land, and that way they could land. So it's 2 out of 36, which reduces to 1 out of 18. Always reduce your fractions. If you don't know how to reduce your fractions, have a calculator with the fraction to decimal. It's going to give you like a little arrow fraction decimal key. Your graphing calculator does it in math, frac, and hit enter. You enter in 2 divided by 36 and go math, frac, enter on a graphing. If you have a scientific calculator, you're looking for this, you enter in 2 divided by 36 and then get to that key and hit equals. If you don't know how to reduce using your calculator, go to the tutors and they'll show you, or they'll show you on a graphing calculator, and ask for a graphing calculator when you're taking your test. But don't use it for the first time on your test. Make sure you take your practice test with it. So now, what if I wanted, let me let me just look at this. What if I wanted the probability of me getting a sum of 4? A sum of 4 on a pair of dice. Then I need to think through this. I could get a 2 and a 2, and I don't want to make every one of them, but I can get a 2 and a 2. I could get a 1 on this one and a 3 on this one, or I could get a 3 on this one and a 1 on this one. Those are 3 different landings of the dice. Then my probability of a sum of 4 would be 3 out of how many ways can a pair of dice land? 36. And I would need to reduce 3 goes into 3 once, 3 goes into 36, what, 12 times. So your probability would be 1/12, or 1 out of every 12 rolls of the dice I would expect to see it. Okay. Or as I rolled more and more, it would be 1/12 of the time. All right, now let's look at, I want to look at rolling a die and flipping a coin at the same time. So I'm going to roll a die and flip a coin. Now that's called an event. It's me doing something. That's what I'm doing. So I'm going to look at that event of rolling a die and flipping a coin. This is called my sample space. It's every possible thing that can happen. Oh, I'm sorry, this is called an experiment. Excuse me. The experiment is what I'm doing. The event is every single thing that can happen. One event is that I could get a 1 with tails. All right, my experiment is I am rolling a die and flipping a coin. Now, that's my sample space. Notice if I roll a die and flip a coin, there's 1, 2, 3, 4, 5, 6. And 6 is, there's 12 possible things that could happen. There's one of them, 5 and heads. See it? It's right there. There are 12 different things. Well, I knew that because how many things can happen when you roll a die? 6. How many things can happen when you flip a coin? 2. 6 times 2. I knew by my fundamental counting principle that there would be 12 things. Again, if you went 6 ways the die could land, 2 heads, tails, heads, tails, heads, tails coming off of each of them, you would see that there's 12, and I listed them. Now let's talk about probability. What's the probability that you would get a 3 and tails? So I'm looking for 3 and tails. The probability that I would just toss those down and get 3 and tails would be, well, let's look. Let me look up here. 3 and tails. Do you see that there's only one way out of 12? So I know that it's 1/12. Now let's say you didn't want to draw out the sample space. If you don't want to draw out the sample space, then you want to ask me for a formula. What do I do? Well, here's the key in probability. When you see and in probability, that means you want to multiply your probabilities together. So if I have 2 events that are going on, 2 experiments, or it's an experiment and I'm doing 2 things, then I would say if I want the probability of getting a 3 on the die and tails on the coin, I would say it's the probability of a 3 times the probability of tails. The probability of a 3 on this die is 1 out of 6. The probability of tails is 1/2. Notice 1/6 times 1/2 is 1/12. So if you're not looking at your sample space, you just need to remember and in probability, you've got to multiply. Okay, now let's look at or with probability. What is the probability we would get 4 on the die or tails on the coin? I just need a 4 on the die or tails on the coin. Now let's find 4 on the die. I got a 4 there. I got a 4 there. Now what about tails? I got tails here, 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 here. Well, then out of my sample space, I see that there are 7 ways to get what I want out of 12 equally likely things that can happen. So I know my answer is 7/12. Now, mathematically, how am I going to do that if I don't look at the sample space? What if I don't want to draw that out? Well, the key thing in mathematics is you want to add when you see the word or. But I'm about to teach you a little lesson with this. add when you see the word or. So that would be the probability of a 4 plus the probability of tails. The probability of a 4 is 1 out of 6 plus my probability of tails is 1/2. Now let me get a common denominator. My common denominator would be 12. So I'm going to multiply top and bottom by 2 and I get 2/12. Top and bottom by 6 and I get 6/12. And notice if I do 2/12 plus 6/12, that is 8/12, not 7/12. But I'm looking up here and I see it is 7/12. Well, when you're doing or, you always have to look for an overlap. Because what happened is, when I found the probability of getting a 4, I found that it was 2 out of 12 times, which is 1/6. There they are. The probability of getting tails was 6 out of 12 things that could happen, which is 1/2. And when I added those, I actually counted the 4 and tails twice. Once here and once here. So you have to subtract the overlap if they are not what we call mutually exclusive events. If events are mutually exclusive, that means they cannot happen at the same time. In this case, if I'm flipping this coin and rolling this die, and I want the probability of 4 or tails, you need to ask yourself, wow, look at that. Did I set them down or did I roll that? And that's weird. Okay, maybe I set them down that way, I don't remember. But if you're looking for the probability of getting 4 or tails, you need to say, well, I could get 4 and tails. If you can get 4 and tails at the same time, then you're going to count it twice. So what do you have to do? You have to take away the probability of 4 and tails. That's your formula. Your formula is, if I want, I'm going to write your formula in this space. Oh, this is getting messy. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. But don't get bogged down by the formula. There it is, but don't get bogged down if you just go, hey, think of this sample space. It's the probability of the first thing plus the probability of the second thing minus, could there be an overlap? It would be the probability of it happening at the same time. The probability of getting 4 and tails, probability of 4 is 1/6 times, because that's and, probability of tails is 1/2. 1/6 times 1/2 is 1/12. And would you look at that? 2/12 plus 6/12 is 8/12 minus 1/12 gives me my 7/12 probability. So don't forget, if you do not have mutually exclusive events, you've got to subtract the overlap. And hopefully you've done problems like this already, so you know what I mean. Now, what if I have a single draw? Oh, and let's just talk about mutually exclusive real quick. If I talk about something that would be mutually exclusive, because this was not, since I could get 4 and tails, that's not mutually exclusive. They could happen at the same time. Something that is mutually exclusive, could you get a red card and a spade with one card? Could you get a red card and a spade? No, they can't happen at the same time. That would be called mutually exclusive. Okay. Now, let's look at, I want to look at some just quick probability problems to show you that I just think about these problems. If you just think, with a single draw of the cards, what's the probability you would get a card that is red or a queen? Well, how many red cards are there? 26. Or, so I'm going to add, how many queens? 4. So there's 30 out of 52, right? 30 out of 52. No. Why is that not right? Because when you counted your red cards, here are your red cards. There were 26 of them altogether. You counted your queens. There are 4 of them altogether. The problem is that when you counted your red cards, you counted the 2 red queens. When you counted your queens, you counted the 2 red queens. Those are not mutually exclusive. You can get a red card that's a queen, which means I have to take away the overlap. The 2 cards that I counted twice, Queen of Diamonds, Queen of Hearts, Queen of Diamonds, Queen of Hearts, I need to take that away. So it's 26 plus 4, 26 red plus 4 queen, minus the 2 red queens I counted twice. So that would be, what is that, 26, 30, that's 28 out of 52, which is 7 out of 13. I had to do this old school and divide top and bottom by 4. All right, what's the probability of finding a heart or a black card? Now it's a single card, so I'm just going to do out of 52. How many ways can I get what I want? A heart or a black card. That's going to be 13 out of, 13 plus, how many black cards? We have 26. That's going to be 39 out of 52, which is 3/4 of the deck. 3/4 of the deck is either a heart or a black card, because the only ones that aren't are the diamonds, and that's 1/4 of the deck. So that would be 3/4 that are. Now, this you have to think, okay? We have to think. My probability of getting a red card and a queen. Now remember, I'm only drawing 1 card. What is the only, because sometimes you are doing all of these things and you're not thinking about the instructions. These are the ones people miss. If you're only drawing a single card and I say, what's the probability of getting a red and a queen? I don't want to multiply anything here because only one thing's happening. I'm drawing 1 card. How many cards are red and queen? Those. So there are 2 of them out of how many cards total? 52. That would be 1 out of 26. So you have to think about that one. Don't get tricked. You need to just say, well, what's the only way I'm going to get a red and a queen on a single draw? That would be 2 out of 52. Now think about this one. What's the probability that you would get a heart and a black card? A heart and a black card. Well, guess what? If you're only drawing 1 card, it ain't happening, which means your probability is 0 because there is no heart that's a black card, so there's no way. Whereas here, like a red card and a queen, you could get a red queen. There is no heart that's black, so you're not going to get a red and a black card with a single draw. So read your instructions. If it says single draw, you have to actually think through that. Okay? Now, this is kind of one of my favorite things. Actually, I have to tell y'all, before I go on to this, I have to tell you one thing before I forget. I love dice. I have dice bracelet. I have dice necklace. I have dice earrings. All kinds. I have crystal dice in my office. I love the dice. Love, love, love dice. So whenever I teach this in class, like whenever we play craps, I wish you were in my class, in my face-to-face class, because we're going to play craps. And when we play craps, I always wear those dangly little dice earrings that face 7. 7's what faces you whenever I'm wearing them, and 7 is the most likely sum to get in a pair of dice. So you need to look that up. Remember, Google the dice images. But anyway, you don't get to see how cute I look, but know that I look very cute with my dice earrings and dice bracelet, dice necklace. I also wear a Las Vegas t-shirt. I guess I need to paint my nails red for them too. All right. I wonder what y'all think. All right. Let's talk about lottery. If you are playing the lottery And I want to know, what is the probability that you would win in the state of Texas playing the lottery? Now remember, in the pick six game, it doesn't matter what order. For example, if you pick 1, 15, 30, 42, 45, 50, you bubble them in on a Scantron, that's one 6-number combination. How many of those 6-number combinations are there? Notice I'm calling it a combination because I don't care what order they come up for pick six. If they draw the 50 ball first, and then the 30, and then the 15, 1, 42, 45, you just won the lottery. So this is a combination problem. Now when Texas started, we actually had 50 numbers in the Texas lottery. And that gave us, you can do it on your calculator, but I've already done it. That gave us 15,890,700 possible combinations. So if you bought one lottery ticket, your probability of winning is 1 out of almost 16 million. If you bought 10 lottery tickets, it'd be 10 out of almost 16 million. But Texas started competing with Louisiana because the people in Texas started going to Louisiana because they have something called a Powerball lottery. And their lottery starts at a $40 million jackpot. So in Texas, we don't think a 1, a 2, a $10 million jackpot is enough. And ours gets high sometimes, or it did, but not that high. But guess what? Our jackpot gets high now because what the Texas Lottery Commission did was they added 4 little numbers. Those 4 little numbers did not keep anyone from buying lottery tickets who were already buying lottery tickets. But what they did was they added, now look at this because it's crazy, they added almost 10 million combinations to the 6 numbers we could pick. Just adding the numbers 51, 52, 53, and 54 to the grouping. Isn't that crazy? So now when you bought one ticket, or when you buy one ticket, you have a 1 out of almost 26 million chance of winning the lottery. You know what? There's only, I had looked it up, I think there's like 21.8 million people in the state of Texas, and not all of us buy a lottery ticket. Some people buy more, but more, you know, like some people may buy 5 tickets, but there's a lot of people buy no tickets. Well, with almost 26 million combinations, what that does is it causes no one to win the lottery over and over and over. And when no one wins, the jackpot goes up. So it keeps us in Texas instead of going to Louisiana to buy our tickets, because look, here's why Louisiana can give out those huge jackpots. This is crazy. In Louisiana, you pick 5 from 69 numbers. So I would say, out of 69 numbers, how many ways can I pick 5? And if you look at that, this is crazy. It's 11,238,513. Well, that's not bad, except here's the kicker in Louisiana. To win their Powerball jackpot, you have to pick this and pick a number from 1 to 26. Now, how many ways can you select a number? And this is your Powerball number, so it's different. You have to pick the winning combination, which you have a 1 out of over 11 million chance of doing. And remember what we do in probability with and? You multiply. I've got, how many ways can I pick a number from 1 to 26? Well, there's 26 ways. I could pick the 1, or I could pick the 2, or I could pick the 3. So when I multiply that times 26, watch this, y'all. 292 billion, okay? 201 million, oh no, I'm sorry, that's million. 292,201,338, 338. Sorry about that. It's really late. All right, but I just want to tell you this because I looked it up. Your chances of winning the Louisiana Powerball with one ticket is 1 out of about 292 million. Just so you know, I looked up on the National Weather Service website what your probability of being struck by lightning was in your lifetime, and it's about 1 out of 13,500. When you divide that by 13,500, you're going to see that you are 270 times more likely to be struck by lightning in your lifetime than you are to win the lottery in Louisiana if you buy a ticket. Isn't that crazy? But people win it, but not all the time. They go with no winner, because that's an awful lot of ticket combinations. So they very often they have no winner. But they do have $1 million jackpot, I think, for the first 5 numbers. I don't know. You have to look at it. I Googled it. It was quite interesting, actually. I like that. I like looking things like that up. Okay, we got to get this finished. Now I want to talk real quick about odds. The difference between odds and probability. And yes, y'all, there is a difference between odds and probability. I want to show you what it is. Let's look at, these are lottery tickets. And by the way, at my office, I actually have lottery tickets so you can see. On the back of a lottery ticket, when you read it, it'll give you the odds in winning. They will never give you the probability. It always says the odds. I'm going to tell you why. If I want to look at the probability of winning, if these are all the tickets, if I'm just going to throw them in a hat and you're going to draw from them, the probability of you winning is there's one winner. It's what you want out of how many things can happen all together. 5 tickets. There's 5 different tickets you can choose from. Only one is a winner. That would be the probability of you winning this lottery. Now, the odds of you winning this lottery, I'm going to throw these tickets again in a hat. The odds are how many ways can you get what you want to how many ways can you not get what you want. So your odds of winning are 1 to 4. Now, why do I want to stress the point that these are different? Because when people look on the back of the lottery ticket and they see 1 to 4 are your odds of winning, they think 1 out of 4 tickets are winners. But they're not. The Texas Lottery, if your odds are 1 to 4, the Texas Lottery Commission is printing 1 winning ticket out of every 5 tickets total. So there's 1 winner for every 4 losers. But our mind goes to, if it says 1 to 4, we think it's 1 out of 4. It's not. Odds of 1 to 4 is 1 out of 5. Now, what if I add another winner? Let's look at the probability of winning this jackpot. Well, if I throw these in the hat, the probability of you winning would be 2, because there's 2 winners, out of 1, 2, 3, 4, 5, 6 tickets total. Your probability of winning is 1 out of 3. So 1 out of every 3 tickets are winners. Okay, that's your probability. Now let's look at our odds. Your odds of winning would be 2 winners to 4 losers. Your odds are 2 to 4. Now you always reduce your odds just like you always reduce your probability. 2 to 4 means 1, 2 goes into 2 once, 2 goes into 4 2 times. Your odds of winning are 2 to 4, which means there's 1 winner for every 2 losers. Now, look at this. If you see a ticket that says your odds are 1 to 2, the average person is going to see that and say that means 1 out of every 2 tickets are winners. That's not what that means at all. If you have a odds of winning are 1 to 2, that means there's 1 winner out of every 3 tickets. 1 winner for every 2 losers. Okay? Now, let me just do a couple of problems real quick. What if I tell you the probability of winning something is 3 out of 7? To get the odds, you would say there's 3 ways to get what I want. To how many ways could I not get what I want? Well, since this is a total, 3 of those are winners, which means 4 of those would have to be losers. So it's 3 to 4. If your probability is 3 out of 7, your odds would be 3 to 4. What if I give you the odds? If your odds are 5 to 7, what would your probability be? Well, your probability would be 5 ways to get what I want out of 5 plus 7, 12 total. So your probability would be 5/12. That's how you go back and forth between the two. I have the formula written up here, but I think the formula is more confusing to students than if you just understand what's going on. Now I need to say one other thing. If your odds of winning are 1 to 4, your odds against would be 4 to 1, which means there's 4 losers to every 1 winner. Your odds against here would be 2 to 1. If your probability of winning is 1/3, your probability of not winning would be 2/3, because you're either going to win or not win. If your probability of winning is 1/5, your probability of not winning would be 4/5. Okay? But I want you to know odds against, you just switch them. Don't forget, with probability, you always have to reduce the fraction. With odds, you always have to reduce as well. Okay? Now, I also, gosh, I don't know how long this is, but I really want to do this real quick because I know you're going to have problems like this. What if I want the probability of you getting a full house with 3 queens and 2 kings? Now that would be called a full boat if you watch Texas Hold'em. Here's what I need. I need 3 queens and 2 kings. That tells me I'm going to be multiplying right there. Now, if I want the probability of being dealt that, I'm going to say, out of 52 cards, how many ways could you hand me 5? And if I do the out of 52 cards, how many ways could you hand me 5? That's 2,598,960. Now on top, I need to find out how many full houses exist that are 3 queens and 2 kings. There's one of them. Here's another one of them. Here's another one of them. I have to find out how many of those there are. Well, I'd say how many ways out of these 4 queens can you pick 3? I don't care about order, because if you pick these, that's the same as picking these. That's why I'm doing a combination. I don't care about the order you get them in. I just want to know how many ways you can get 3 queens. When you do that combination, you're going to get 4. And it makes perfect sense, because look at this. How many ways can you pick 3 queens? You can pick all but the queen of clubs, all but the queen of spades, all but the queen of hearts, all but the queen of diamonds. There's 4. Now, I'm going to pair those 3 queens. You'll see why I'm multiplying, because how many ways could I get 3 queens? There were 4. So I could get the queen of hearts, queen of diamonds, queen of spades, queen of clubs. I list them. Now with those, I'm going to go, okay, I'm going to put with those 2 kings. How many ways can you get 2 kings? I don't care the order. If you get the king of hearts, king of diamonds, that's the same as king of diamonds, king of hearts. So I'm going to say, out of 4 kings, how many ways can I give you 2 of them? And when you do that on your calculator, you're going to get 6. There's one way. There's another way. There's another way. There's another way. And if you do it, you're going to see the 6 ways. Okay, I want you to see what I'm doing. So I'm going to pair. There are what, 6? So each of these 3 queens will be paired with each of these 6 ways I can give you the 2 kings. So that's going to be 24 out of 2,598,960. When I divide top and bottom by 24, that's actually 24. When I divide top and bottom by 24, what did I get? I think I got this. 1 out of 108,290. So the probability that you would be dealt any 5-card hand that was a full house, queens over kings, you always say whatever it is you have 3 of over what you have 2 of. Even though those are lower than the kings, I say queens over kings. This is a full house, queens over kings. The probability you would be dealt that in a 5-card hand is 1 out of about 108,000. Not real good, okay, that you would be dealt a full house with queens over kings. Now, what's the probability you would be dealt this exact hand that you're looking at? Well, and I don't care what order, this is the same 5-card hand. This is a 5-card hand. Do this with it. It's the same 5-card hand. The probability you would be dealt these exact 5 cards is 1, because there's only one of these 5 card hands. There it is. 1 out of the 2.5 million. Okay? All right, so you can do a problem like that now. I want to look at one other symbol. We're almost done. The probability of a club given, it shrinks your sample space, given that you got a black card. Now this is actually really important, like you'll hear it in medical science, the probability that you will have a heart attack given the fact that you're a smoker. What they do is look at only the smokers and see over time, out of the smokers, how many of them had a heart attack. And that's your empirical probability of having a heart attack. In medical science, sports, all of that is based on empirical probability. Okay, hopefully you read about that when you were doing this. This is a review. Probability that you get a club given that you were given a black card. Well, if I gave you a black card, I shrunk the sample space. Am I dealing from a 52 card deck anymore? Well, no, you got a black card. That means I know you got one of 26 cards. These 26 cards. You got one of these. You're sure it's black. So if you know it's one of these 26 cards, what's the probability it's a club? Well, how many of these black cards are clubs? 13 out of 26. If you know that your card is black, then the probability that it is a club is 13 out of 26. Oh, that's 1/2. Sorry. Whew. I'm glad I caught that. Now, there's probably things in here I didn't catch. I'm sorry, y'all. Again, it's late. So what this does is shrink your sample space. Again, let's look. Let's say I have you pick a card out of a deck of cards. And I say, what's the probability you got a queen? And your best friend is beside you and they nudge you and say, hey, I saw your card. It's a face card. Then you have some knowledge. You say, hey, if it's a face card, I know it's one of the jacks, queens, or kings. The only cards that are face cards are the ones that have faces on them, y'all. Aces are not face cards. They're high cards. A face card has a face. Okay? So if you know it's a face card, it's either a king, queen, or jack. How many of each are there? 4 kings, 4 queens, 4 jacks. There's 12 possible cards it can be. So you're no longer thinking about the whole deck of cards because you know that it's a face card because your friend saw it when it was sliding into you. So what's your probability that you have a queen in your hand? You're going to tell me, hey, there's 4 queens out of, I know it's a face card because my friend saw it. It'll be 4 out of 12 or 1 out of 3. Okay, I hope that helped. I did it as fast as I could. I really hope you do well on this test. It's really fun stuff, so I hope you enjoy doing the review and the practice test. It shouldn't be grueling. It should be kind of fun. Really, you could be graphing parabolas, but you're not. We're looking at cards. We're looking at dice, Scrabble tiles, talking about little cars moving around, and Dodo and Foxy. You're welcome for Foxy. I was trying to think of a cool word. I thought Foxy was kind of neat. Winning and losing in the lottery. So I think this is kind of interesting. I hope you do too. Actually, probability is my absolute favorite branch of mathematics. So I love teaching finite math because I get to go really dive into all of this stuff. Okay, good luck on your exam, and I'll see you in the next video.